Section 7, and I'm going to start out here and mention that if you're following along with the original PowerPoints, they kind of swapped the information on the first couple slides here, so I've fixed it, but they're not fixed on the version that you might have. Anyway, we're going to be looking at changes of states, and hopefully that is familiar to you. However, there is something that might be new here, and that is during the change of state, as a substance is transitioning from one thing to another, the temperature actually plateaus. You have a constant temperature during the change of state itself. Anyway, we'll get into looking at that here in a moment. So changes of state include melting and freezing, boiling and condensation, both of which you're probably familiar with. I will point out that unfortunately we have names for both the forward and reverse process, and so as we are heating, it would be melting and boiling, and actually sublimation here, which I haven't mentioned yet. As we are cooling, it would be the other three then. Cut out pen color change, freezing, condensation, and deposition. Now these last two here you're probably less familiar with. Now this pair here you're probably less familiar with unless you think of dry ice, and even then it tends to be just the sublimation process going from a solid to a gas that you're familiar with, and not the reverse process of going from a gas to a solid. But some substances, if the conditions are right, and some substances just naturally under normal conditions will skip the liquid phase, and so that one might be new to you, and of course it depends on the substance, it depends on the conditions as to whether that can even. So melting and freezing is where we go from solid to liquid, or vice versa, liquid to solid, and for water this happens at 0 degrees Celsius. Now we want to point out that when you are melting, we are adding heat to the substance, and when we're freezing, we're taking away heat from the substance. That means it's actually giving up heat energy, which may sound strange, but you always have to put yourself in state of mind of the substance that you're looking at when you're thinking about thermal interactions. And so if we want to go from being a solid to a liquid, then energy has to be taken in, and now I have that energy. The particles are able to vibrate more freely and break bonds with one another's sometimes, and so now we have a liquid. If we're going to go back to a solid, then that energy has to be given up. That heat transfer is called the heat of fusion. It's the amount of energy that it takes to turn 1 gram of a solid to its liquid at its melting point. For water, that's 80 calories or 344 joules at 0 degrees Celsius. And so if we add in this heat energy, sometimes that'll be added in as a delta H, then we will go from having solid water to liquid water. It's also the same amount of energy, heat energy that has to be removed to do the reverse process. As a side note, sometimes you will see that here, where instead of having the heat over on the product side, the right-hand side of a reaction equation, we've not really gotten into how to read reaction equations yet, you will instead have the minus the heat energy, the delta H here, instead of having a plus on the other side. That's just like in math where you can move it from one side to the other, but I thought I'd mention that does occur. What this means, though, is because these two are equal to one another, we can use them as conversion factors, and of course, because we have it in 2 different units, it actually gives us 4 conversion factors. And so if we want to calculate the amount of heat needed for melting or the amount of heat released when freezing, we can also set up this equation, although I like to think of it in terms of just doing the dimensional analysis with the units. I don't tend to think of or jot down that formula. I just know what I started with and my conversion factor and can get to what I want to end it with. So how many kilojoules are needed to melt 32 grams, that's a mass of ice, at 0 degrees Celsius. So we have 32 grams of water, and we know that the heat of fusion for water from the prior slide is that it takes energy, joules, to convert that and that is 334 per 1 gram of water. And then we know, of course, that there's 1,000 joules and 1 kilojoule. And at this point, it's punched into a calculator and going to round it off to 3 sig figs because we didn't use this value here. So we're stuck with using this one, and we don't let our conversion factors limit us. Plus, it happened to have 3 anyway, but 10.7 kilojoules of energy. As I mentioned, sublimation happens when a solid turns directly into a gas and skips the liquid phase. Again, any phase transition, there is no change in temperature. The temperature plateaus for the substance, and the reverse process is called deposition. They mentioned here, as I did a moment ago, that dry ice is your example of something that goes through this process. It's why we call it dry, because it doesn't create that liquid there. Although it also turns out that water does do this. It's why you get freezer burn and frost building up on the inside of a freezer, is because the ice in your freezer is actually at those low temperatures going through the sublimation process. It is turning into a gas, and then that gas in the freezer is refreezing in other locations inside the freezer, and so then that's your deposition process. Some of that also has to do with just how frequently you're opening it up and some moisture from the air getting in there as a gas, and then it's also going through the reverse sublimation, that is deposition process. We have here evaporation, boiling, and condensation. And I'll be honest, this was something that I didn't get for a long while because, unfortunately, my teacher who taught me changes in state used these two interchangeably. And what happens is, because you have particles moving around randomly within a container, on occasion, with something like water or any other thing that can evaporate, you'll have a particle that gets close to the surface that has enough kinetic energy that it just naturally is able to break free. That there is evaporation. Going from a liquid, or as I mentioned in the freezer situation, even a solid, to a gas can happen because essentially the way I think of it is that particle that has enough kinetic energy, its individual temperature is high enough to boil. Even though the bulk of the substance, its average temperature, isn't high enough to boil. Now, if you get to warmer temperatures, more can evaporate, and eventually you get to a point where all of them have to evaporate, and that's what we call boiling. But you, of course, know that if there's a rain puddle outside, that puddle will eventually evaporate, and the water there goes away, and the surface is left dry. And yet, the outside temperature didn't have to get up to the boiling point, that is 212 degrees Fahrenheit or 100 degrees Celsius, and that would kill all life. And so it can't be that it is heating up to the point where it is boiling. And so it naturally, over time, some will evaporate. Different temperatures allow for more or less evaporation happen. Cold temperatures, only a little bit of evaporation happens. Warm temperature, a lot of evaporation happens, which is why the air tends to be drier in the winter and more humid in the summer. It has to do with the amount of moisture that the atmosphere can contain, and that in and of itself has to do with how much the atmosphere is expanding and contracting a little bit, and essentially how many spaces there are for the water molecules to get in there, as well as the just natural temperature of the stuff that would evaporate is colder to begin with, so you have fewer pieces that are actually able to escape. Condensation is the reverse process, where the heat is removed. Of course, outside, that's what you experience as dew, especially in the warmer seasons. In the colder seasons, that dew not only condenses, but then goes through the freezing process and as well, and you end up with frost. Just like we have a heat of fusion for the change in state from a solid to liquid, there's a heat of vaporization for the change in state from liquid to gas, and vice versa. For water, that's 540 calories, or 226,000 joules. You'll notice that's significantly higher. It's part of why it takes longer for water to boil. It has this high heat capacity, and then even once you get it up to there, it takes a lot more energy to do that vaporization process, to get it turn into a gas, to get it to boil away. And so, once again, we have the amount of heat that needs to be added. If we're doing the reverse process, sometimes called the heat of condensation. I think of it as just a negative of the heat of vaporization. It's the same amount of energy just being released instead of being absorbed. And once again, they can be used as conversion factors. You can take a moment and jot them down if you want. We're going to dive right into a practice problem over this, though. So how many kilojoules? That's the heat that we're wanting to solve for. In 50 grams of steam, that's a mass from a volcano, condenses at 100 degrees Celsius. So we have 50 grams of water, and we know that the heat of vaporization of water is, in the joules units, is 2,260 joules per 1 gram of water. Probably should have put my water here, and now those two cancel out. We're left with joules, but we don't want joules, we want kilojoules, so we have to do the 1001 conversion there, and then that will cancel out joules. And we'll be left with kilojoules, which is what we want as a unit. So punch that into a calculator, and again with 3 sig figs, we end up with 113 kilojoules. I'm not going to be picky with this, but I will point out that because the question says it was released, then 113 is okay. If we wanted to talk about the heat change instead of it specifying whether it's the amount of heat absorbed or released, technically because it's being released, it is a negative answer there. Again, I don't care if that negative sign is there or not. I'm pretty sure your textbook doesn't want the negative sign, so avoid that when if you're doing the online homework. But I did think I would mention it. If you go on to take more chemistry, some teachers are picky about that. We can graph these changes in what's called a heating curve. And on a heating curve, we have regions where we have a substance changing its temperature. And yes, you can memorize this. I tend to just think through it because over here is my temperature, and down here is the amount of heat, or sometimes it'll just be graphed as time if the amount of the rate at which the heat is being added is consistent. And so if I'm cold, well, I'm going to have a solid. And then once I warm up, I'm going to have a liquid. And then once I warm up, I'm going to have a gas. And so I don't memorize these. I just think through it like that. Of course, you can think through the reverse process as well. Hot as a gas, and then liquid and solid. But then because these changes of state happen at constant temperatures, as we've mentioned already, then these regions here where we have a mix of states of matter are plateaus. And so the boiling, or if we're doing the reverse process, the condensing, the melting, or if we're doing the reverse process, the freezing, where we have both states of matter, here it would be liquid and gas, here it would be solid and liquid, the temperature plateaus. For water, that is, liquid water can't be colder than 0, but solid water can't be higher than 0. And same thing up here with the boiling point at 100. And so as we're trying to convert the substance from one temperature to another, and we keep adding in heat energy, the temperature will go up, and then that temperature will plateau. And then once we've changed it all, if we're going from solid to liquid that's melted, once we've melted it all, then the heat can start to rise again, or temperature can start to rise again. And then once we get up to where it's hot enough that it begins to boil, then we'll have a liquid and gas being formed, but the temperature will plateau for the mixture then until it all boils away, and then we can start increasing the temperature of the gas there. Cooling curve is just the same thing in reverse. I'll let you pause and take a moment to look at it if you want to convince yourself. I will say that here they added the states of matter here over the plateaus. So a plateau, horizontal line on a curve, change in temperature? No. If you just read the y-axis, plateau, it's staying at the same y value. So that would be constant temperature, and that happens at a change in state. So sneaky question here, 2 correct answers there. And a slope on the curve then represents the one that we didn't have up above, the change in temperature. These other 2 are not occurring there. This one here specifies for a cooling curve. It really wouldn't matter which one we are looking at, but water condenses at a temperature of 100 degrees Celsius. At a temperature of 0 degrees Celsius on a cooling curve, it's going to freeze. So I suppose there it does matter that we have a cooling curve. If it was a heating curve, then it would be melting. That one's just flat out wrong. At 40 degrees Celsius, it is a liquid, and when it is freezing, we are removing heat energy. So 175 gram sample of steam, that's of course gaseous water, at 100 degrees Celsius is emitted from a volcano. It condenses, so it's going to turn to a liquid, cools and falls as snow, so it's going to turn to a solid at 0 degrees Celsius. And then we have how many kilojoules of energy are released. So we're looking at a cooling process. So I'm going to draw here real quick a cooling curve, and the water's cooling curve looks something like this, not the scale, just a rough sketch here. And we are starting here at steam that's at 100 degrees Celsius, and we're ending here at water ice that's at 0 degrees Celsius. And so we are interested in 3 legs here of the change. And so that's going to involve a calculation for each of those segments. So in this section, we've done the red one already, or at least that kind of calculation, where we know it takes 2,260 joules per 1 gram for the heat of condensation, the amount of heat released as it condenses. Then for the liquid water, we could do a conversion factor there, but it's better to use the specific heat formula in this particular case. M times specific heat times the change in temperature. This is from the prior section, and this will take care of our cooling process for the water, and then we'll do the heat of fusion, which is 334 joules per gram of water for the final segment. So taking each of those one at a time, we know that we have 175 grams of steam or gaseous water, and we know that 1 gram of water releases 2,260 joules, and we want this in kilojoules, so of course there's 1,000 joules in 1 kilojoule. And then the joules cancel out, the grams cancel out, and we're left with kilojoules, which is what we're expecting, and that gives us 396 kilojoules. Using the heat formula, I labeled it specific heat a moment ago. It probably should have just been heat because the conversion factor there is specific heat. But we have 175 grams times by the specific heat, which is the 4.184 joules per gram degree Celsius. And that degree Celsius there, having 2 units in the denominator, is part of why the dimensional analysis method is a little bit harder. And the change in temperatures is going from 100 degrees Celsius. It's going from an initial temperature of 100 and a final temperature of 0, so that's technically this here. However, since we're told it's heat released, and this is where I said the negative thing doesn't really matter, you're going to have to think of this as the heat and not the change in heat that's released there. And so you can kind of think of this as being inside absolute values, and we're going to use 100 here. And here we end up with 73.2 kilojoules. And lastly, we'll do a calculation that's similar to the first one, except we have just a different conversion factor there. That 1 gram of water releases 334 joules of energy. And once again, the 1,000 joules to 1 kilojoule conversion. Joules cancel, grams cancel, and we're left with kilojoules once again. And that gives us 58.5 kilojoules. And then the last step, because we want the whole thing, is to add all 3 of those together. And when we do that and round with sig figs, we get 528 kilojoules, which is that there. And had we been asked to handle the other 2 segments here, had it been steam that started out hotter than 100, or had the ice continued to cool, the snow continued to cool, then we would have to know the heat capacity of, or go back and look up the heat capacity of water in different states of matter, but then we would just add each of those there as well. And of course, if you're only looking at a separate segment, maybe we only go from gas to liquid at this temperature, then we're just doing fewer of these, and of course having a different temperature in there. But that should get you through any kind of calculation like this you're going to need. It's just going to take a few steps, though they aren't that hard. It's just combining these calculations we've already been looking at. That finishes the chapter. As usual, there's a concept map here if you want to take a moment and read through that. Feel free to pause, but otherwise, if you have any questions, be sure to let me know.